Okay. Today we turn to study eigenvalues and eigenvectors of a matrix. Given a square matrix, that means that the matrix, the number of the rows and the number of the columns are equal, then the matrix is a square matrix. For eigenvalues and eigenvectors, we only consider square matrices. Given a square matrix and a vector, then the matrix times the vector is a vector. Yeah, a matrix times a vector is a vector. In general, this new vector is not parallel to the old vector. Say, for example, say, example. Then matrix A be 3, -2, 1, 0, 2 by 2, and vector V be -1 and 1. Then A times V is -5, -1. A times V is this vector. But this new vector not parallel to this old vector. How to see that? Plot these two vectors on the XY plane. Yeah, let me plot. These two vectors are two-dimensional vectors, so plot them on XY plane. -5, -1 is, suppose that -5 is here, -1 is here. Then A times V, this vector is arrow. This arrow. This is A times V. V, -1 and 1. Say -1 is here, 1 is here. So V, this vector is this arrow. Is this arrow. See, these two arrows, they are not parallel. So in general, this is true. Okay, A times a vector is not parallel to the original vector. But there are some special vectors. A times the vector is parallel to the original vector. There are some such vectors. Say, for example, let me still pick this matrix A. A second example, say, let A be 3, -2, 1, 0. And take a look, this vector, 2, 1. Then matrix A times this V is this vector, 4, 2. But 4, 2, let me take out the number 2. Then 2, 1. 2, 1 is the vector V. This is 2 times V. Now this time, A times V is parallel. Now this time, A times V is parallel to V. How to see that? Plot the graph, plot these two vectors on XY plane. on xy plane. Okay. Vector v, 2, 1. So suppose that 2 is here, 1 is here. Then this arrow is vector v. Yeah, this is a vector v. Vector v. A times v is 2 times vector v. 2 times. So the length is double the length of this vector. So let me use a different color. Yeah, double. Yeah. So this is a 2 times v. Yeah. So these two vectors are parallel, but this vector is a special vector in general. For any vector, arbitrarily pick a vector, usually A times v, not parallel to v. Okay, for this special vector, we call it because A times this vector is parallel to the original vector. We call this vector an eigenvector of this matrix A. How about this number 2? We call this number 2 is the associate with this vector v, associate eigenvalue of matrix A. When A times v is parallel to v, the v is called an eigenvector. And this scalar 2, eigenvalue, yeah. So let me present the definition of eigenvalues and eigenvectors now. Okay, definition. Okay, definition. Let A be a square matrix. Okay. Yeah. For eigenvalues and eigenvectors, we only consider square matrix. Let A be a square matrix if a vector. Let me emphasize that this vector is non-zero vector. If a non-zero vector and a scalar lambda satisfy this equation, A times V is lambda times V. Then lambda is called an eigenvalue of matrix A. How about the vector V? And V, an eigenvector associated with the eigenvalue lambda, or we also call V an eigenvector corresponding to the eigenvalue lambda. Okay, yeah, this is definition about what is an eigenvalue and what is an eigenvector. When this equation is true, and vector v non-zero. How about the scalar lambda? Scalar lambda can be zero, can be non-zero. It doesn't matter, but v non-zero. If this equation is true, then the scalar is eigenvalue. The vector is eigenvector. Okay. Yeah. Definition. Always remember, keep the definition in mind. Okay. Always keep the definition in mind. Okay. About this definition, let me make some remarks. Okay. Okay. About the definition. Okay. Remark. Number one, as a convention, okay, an eigenvector is a non-zero. Yeah, this is important. Eigenvector is non-zero. It's a non-zero vector. Okay. Why an eigenvector we require is non-zero? Because if vector v is zero, then a times zero is lambda times zero. This equation is always true for any matrix A and any lambda scalar. This equation always true if v is zero. So this is too trivial, this case, right? When v is zero, this equation is always true, no matter what the matrix A is, what the scalar lambda is. So we exclude the case. Okay. Right. However, about eigenvalues, an eigenvalue lambda can be zero. It doesn't matter. Can be non-zero. Okay. Can be non-zero. Why eigenvalue can be zero? Because when lambda is zero, a times a vector is zero times a vector. Then zero times a vector is zero vector, right? Yeah. This equation, a times a vector is a zero vector, not trivial. Okay, not all matrix A or vector V, their product is zero. No, this is not a trivial case. Okay, for what vectors can make A times V zero, you need to solve this linear system. This is a homogeneous linear system. So lambda can be zero. This is not a trivial case. But vector V is zero. It is a trivial case. Always true. Okay, always true, this equation. So I make remarks about the definition. Okay, first, eigenvector, we assume non-zero vector. But eigenvalue can be zero, can be non-zero. Okay, keep this in mind. Okay, now next, let me show you examples. Take a look at some examples about eigenvalues and eigenvectors. Say example one. For this matrix, 1, 2, 3. The row sum is 6. Row sum means the sum of all the entries in a row. 1 plus 2 plus 3, 6, right? Row sum 6. Then the second row, 2, 1, 3. Yeah, this matrix, the second row, the row sum is also 6. 0.5, negative 1.5, 7. The third row sum is also 6 for this matrix. 5, 1, eigenvalue. We will see a 3 by 3 matrix has 3 eigenvalues. No, 5, 1 here. Okay, 5, 1 eigenvalue. Okay, with no calculation, just by inspection, and justify your answer. Okay, now it means that go back to the definition. Find 1 eigenvalue. Okay, that means that find a number lambda, find a non-zero vector so that this equation is true. Then when this equation is true, the lambda is eigenvalue and the vector is eigenvector. Okay, now let me try to find a vector solution. By observe that the row sums are all 6. So how about let me take this vector. 1, 1, 1. This vector. Yeah, this is a point in XYZ space, but a point in this book, in this course, a point, a vector, they're the same. Okay, yeah, this is a vector 1, 1, 1. This vector. Yeah, let V be this vector. Now let me compute A times V. A times V. 1, 2, 3. 2, 1, 3. 0.5, 7. Yeah. 3 by 3 matrix times a 3 by 1 matrix by row column formula. Okay, then we get 6, 6, 6. Take out the number 6. 1, 1, 1. So it is a 6 times vector V. Yeah, vector V. So when this equation is true, the number is eigenvalue and the vector is the corresponding eigenvector. So therefore, 5, 1 eigenvalue. So 6, this number is 1 eigenvalue of matrix A. Done. 5, 1 eigenvalue. And 1, 1, 1, this vector is an eigenvector associated with the eigenvalue 6. Okay. This is example 1. Now, second example. Example 2. Yeah. Example 2. Okay. Let matrix A be 1, 6, 5, 2. Vector U be 6, -5. Vector V be 3, -2. Now the question is, are U and V eigenvectors of this matrix? I try to answer this question. How to answer this question? Go back to the definition. Okay, yeah. Go back to the definition. Yeah, definition says that when and only when this equation is true, then the vector is eigenvector. Okay, now let me compute. Let me compute A times U. Okay. 6, 5, 2. 6 times 5. 2 by 2 matrix times a 2 by 1 matrix. The result is a 2 by 1 matrix. By row column formula, then I get the vector. It is negative 24, 20. The result. Okay, now let me take out the common factor. Negative 4. Take out negative 4. Then I get 6, negative 5. 6, negative 5 is U. Negative 4 times U. So this equation in the definition is true. Therefore, so U is an eigenvector of matrix A. And the corresponding eigenvalue is negative 4. Then how about V, vector V? Let me see. Compare A times vector V. A, vector V, 3, negative 2. By row column formula, then I get 9, 11. Now, ask yourself whether or not you can find a number. The number times vector V. So that this equation is true. Okay, vector V. Yeah, vector V. 3, negative 2. Let me try to find a number. Okay. Negative 9. From here, we can see that negative 9 is lambda times 3. The second entry, compare. This linear system has a solution. Let me see. From the first equation, lambda should be negative 3. From the second equation, lambda should be negative 11 over 2. So to make this equation true, actually, low lambda can make this equation true, right? Low lambda can make this equation true. Therefore, so conclusion, V is not an eigenvector of matrix A. Conclusion, done. This is a example 2. Now, example 3. Okay, example 3. And let matrix A be 4, negative 1, 6, 2, 1, 6, 2, minus 1, 8. Now, so that the number 2 is an eigenvalue of this matrix. This is a part A. Now, part B. Phi or the corresponding eigenvectors eigenvectors. Find all the eigenvectors associated with this eigenvalue 2. Okay, now how to answer these two questions? Solution. Let me answer part A first. So that 2 is an eigenvalue of this matrix. Go back to the equation. If I can find a non-zero vector v so that this equation is 2, then 2 is an eigenvalue. Okay, it's an eigenvalue. So let me solve. To answer part A, let me solve this equation. Solve this equation for x. If I can find non-zero x, then 2 is an eigenvalue. Okay, solve this equation. Okay, let me rewrite this equation. Move all the unknowns to the left-hand side. Okay. Move this vector to the left side, then the right side is a zero vector. Zero vector. Okay. Now, take out x. Take out x. But wait. If I take out x in this way, then something is wrong. Why? This is a 3x3 matrix. Scalar, you can view scalar as a 1x1 matrix. 3x3 matrix minus 1x1 matrix not computable because these two matrices, their sizes are not equal. So don't take out x in this way, not computable. Then how to take out x? Okay, here. A times x, let me write the second term as 2 times identity matrix. 3x3 identity matrix times x. Yeah. Identity matrix times x is equal to x. Okay, now take out the vector x. Take out the vector x. Now this time, this is a 3x3, and I also 3x3. Now this subtraction is computable. Now this time, okay. Now this equation is this equation. They're the same. They're the same. Okay. Now let me solve this equation. This is a homogeneous linear system. Okay. Okay. Now how to solve this equation? Let me compute the coefficient matrix A minus 2i. Okay. So this is a A 4. Negative 1, 6. This is 8. Minus 2 times I, identity matrix. Okay, a number times a matrix is the number times all the entries. Now make a difference. So we get 2. 4 minus 2 is 2. Negative 1 minus 2 times 0. Negative 1. 6 minus 2 times 0. 6. The same. This is 2. 1 minus 2 times 1. Negative 1. Then 6. 2, negative 1. 8 minus 2 times 1. 6. Yeah. This is a minus 2 times I. Yeah. The coefficient matrix of this linear system is this. Okay. Then we Okay, let me continue my solution on the next page. So we have a minus 2ix x is 0. It is linear system. Coefficient matrix is 2, negative 1, 6. 2, negative 1, 6. 2, negative 1, 6. 2, negative 1, 6. And then the unknown, x1, x2, x3. The right side, 0, 0, 0. Yeah. Now, solve this linear system to see whether or not we have non-zero solution. Okay, how to solve this linear system or augmented matrix? Reduce the augmented matrix augmented matrix to an epsilon form. Okay. Augmented matrix, coefficient matrix together with right hand side, augmented matrix. Okay. Now reduce this matrix to epsilon form. -1 times first row add to the second row. We get 0, 0, 0, 0. -1 times row 1 add to row 3. 0, 0, 0, 0. Yeah. This is an epsilon form. Now, x1, first column corresponds to the unknown x1. Second column, x2, x3. So from the epsilon form, we can see that second column is a free column. It contains no pivot. Third column, also a free column. So therefore, this guy and this guy, they are free variables. Whenever a linear system, the linear system has solution, consistent linear system. When a consistent linear system has a free variable, the linear system has infinitely many solutions. Conclusion. Because there are free variables, the linear system has infinitely many solutions. So therefore, there are non-zero solutions. Okay, go back to the original equation. This linear system has non-zero solution. Therefore, number 2 is an eigenvalue, right? A times a non-zero vector is 2 times non-zero vector. By definition, 2 is an eigenvalue. So conclusion. So conclusion is 2 is an eigenvalue of the given matrix. This is the solution to part 1. Now part 2. Okay, now 2 is an eigenvalue. Find all eigenvectors. Find all eigenvectors. B. To find all eigenvectors, that means that we need to solve this linear system for all x, all non-zero x, for all non-zero. Because eigenvector is a non-zero vector, non-zero solutions. All the non-zero solutions are eigenvectors associated with the eigenvalue 2. From pi, we see that ax is equal to 2x. This equation is the same equation with a minus 2ix. Okay. In pi, we have compute a minus 2i. It is 4, negative 1, 6. 4, negative 1, 6. Yeah. Times x is 0. In pi, we also see that augmented matrix can be reduced to 2, 1, 6, 0, 0, 0, 0, 0. Now in part B, we want to find all the solutions of this equation. So continue. This is a epsilon form, but not in reduced epsilon form yet. Reduced epsilon form requires the leading entry is 1. So scale row 1 by 1/2. 1, negative 0.5, 3, 0, 0, 0, 0, 0. Zero. Yeah. This final matrix is in reduced epsilon form. Now, write the final matrix in equations. In equations, the final matrix is x1 minus 0.5, x2 plus 3, x3 is 0. First equation. Second equation, 0 is 0. Third equation, 0 is 0. Now solve this linear system for the basic variable, only one basic variable in terms of the free variable to get all the solutions. 0.5, x2 minus 3x3. Right. All the solutions, then x2, x3, arbitrary. Yeah. This is the general solution. General solution. Okay, now after we get the general solution, write the general solution in vector form. Why? Because eigenvector is a vector. It's a vector. So write the solution in vector. Okay. In vector, the solution is free. Let me plug in this equation in x. 0.5, negative 3. Okay, so 0.5 x2, negative 3 x3. Then x2, x3. Now split this vector into a sum. Okay, into sum. 0.5 x2. Second entry, there is an x2. Third entry, low x2. So put 0. Then plus second vector. Second vector is about x3. x3. Second entry, low x3. Put 0. Then x3. x3. Therefore, this is a take out x2, 0.5, 1, 0. Take out x3. Negative 3, 0, 1. Yeah. These are all the eigenvectors. Okay, where x3, x2, x free, arbitrary, okay, free, okay, are free, yeah, freely assign values to x2 and x3, yeah. So okay, these are okay. Let me call this equation, okay. The vectors, there are infinitely many, okay. The vectors in equation 1 are all the eigenvectors of matrix A associate with the eigenvalue 2, the eigenvalue 2. Okay. Of course, because eigenvector cannot be 0, so you cannot assign 0 to x2, 0 to x3. Otherwise, the solution is 0. So here, let me emphasize the non-zero vectors in equation 1 are all eigenvectors. All eigenvectors. Okay. Done. This is a solution to part B. Okay. Now, from this example, from what is the number of this example? Example 2. From example number 2, we can see that an eigenvalue has how many eigenvectors corresponding to it? Infinite many. Okay, has infinite many corresponding eigenvectors. Yeah. An eigenvalue has infinitely many corresponding eigenvectors. Okay, now let me put all the corresponding eigenvectors together to form a set. Okay. Okay. This is a definition. Okay. Definition. Okay. Let A be a square matrix, of course. Say size is n by n. And lambda, an eigenvalue of matrix A. So lambda has infinitely many eigenvectors. Right. Now I put all the eigenvectors together. I have a set. That set of all the eigenvectors associate or corresponding to the eigenvalue lambda. Eigenvector is non-zero vector. Okay, put all the eigenvectors together, then we have a set. And also plus the zero vector. Okay, also insert the zero vector into the set. Okay. Yeah. Then all the eigenvectors plus 0. This set is a subspace of Rn, because I assume A is n by n. So eigenvector is a vector in Rn. Okay. So put all the eigenvectors together, then plus 0. This set is a subspace. What do you mean? A subspace. Definition is if the set is closed under vector addition and is closed under scalar multiplication, then the set is called a subspace. So yeah. So this statement means eigenvector plus eigenvector still an eigenvector. A number times an eigenvector still is an eigenvector. Okay. Yeah. This set is a subspace of Rn. We call this subspace called the eigenspace of matrix A. Associated with the eigenvalue lambda. Okay. Let me make a remark about this definition. Okay, the set of all eigenvectors corresponding to eigenvalue lambda plus 0 actually is the set A minus lambda I null space of this matrix. What do you remember the meaning of a null space? Yeah, a null space of a matrix means the set of all the solutions. Let me change this. Okay, yeah, let me change this. Yeah. Null space of this matrix is the set of all the solutions of this homogeneous linear system. This is definition of null space of a matrix. Yeah. So actually, eigenspace is the null space of A minus lambda times I. Yeah. Yeah. This is an eigenspace. Eigenspace of A associated with lambda. So eigenspace actually is the null space of A minus lambda times I. Okay. Yeah. This is from the definition of null space. Go back to the previous example. So in the previous example, yeah, matrix A is this, and part B we have found all the eigenvectors. Now put all the eigenvectors together and plus 0. Yeah. So in this example, yeah, this is a solution to part B. Okay. Now from the solution to part B, we can see that eigenspace of the matrix A associated with the eigenvalue 2, right? Eigenvalue 2, yeah, 2, eigenvalue 2, yeah. Is the set of all the eigenvalues, the set of all eigenvectors plus 0 vector. Okay. The set of all eigenvectors. Now, in part B, we see that all the eigenvectors is spanned by this vector and this vector. So actually, this is a span. The set spanned by these two vectors. Yeah, let me write the first vector as a point to save space. 0.5, 1, 0, and -3, 0, 1. Yeah. So in example 2, eigenspace corresponding to eigenvalue 2 is the set spanned by this vector and this vector. These two vectors, actually, this spanning set is a smallest spanning set because these two vectors easy to be seen. They are linearly independent. If one vector depends on the other vector, we can drop it from the spanning set. But now we cannot because these two vectors are linearly independent. How to see these two vectors are linearly independent? By go back to the definition, solve this equation. Yeah. Alpha 2, yeah. 1 is 0, 0, 0. Yeah. If this equation has only 0 solution, then these two vectors are linearly independent. But easy to solve this, then we see that only 0 solution. So therefore, these two vectors is two vectors. They span eigenspace, and we cannot drop any of the two vectors from the spanning set. So form a basis for the eigenspace. Yeah, these two vectors together is a basis for the eigenspace because the basis contains two vectors. So this eigenvector, the dimension is 2. It is a two-dimensional subspace in R3. Yeah. All the eigenvectors are vectors in R3. So eigenvectors spanned by these two vectors. So the eigenspace is a two-dimensional subspace of R3. This is a topic one. Topic one is about what is an eigenvalue, what is an eigenvector. Keep the definition in mind. Okay, keep the definition in mind. Now, second topic. What is second topic? Oh, in the second topic, I want to show you more examples about eigenvalues and eigenvectors. Okay. Topic 2. More examples. Example 1. Okay. Example 1. Let lambda, it is a scalar, be an eigenvalue of an invertible. Invertible means the matrix has inverse. Invertible matrix A. Okay, so that lambda inverse. This is equal to lambda is a number. Lambda to -1 means 1 over lambda is an eigenvalue of A inverse. Okay. How to answer the question? Solution. Because lambda is an eigenvalue of A. What it means? Lambda is an eigenvalue of A. Go back to the definition. Definition, yeah. Here, definition. lambda is an eigenvalue. That means that this equation is true for some non-zero vector v. Yeah. Since lambda is an eigenvalue, there is a non-zero vector v such that A times V is equal to lambda scalar times V. Yeah. Scalar times V. Okay. Now I came that I first came that lambda is eigenvalue non-zero. Why I came this? Because if lambda is 0, then lambda to -1 is not defined, not commutable. So let me first claim that this number is non-zero. Okay. Why lambda is non-zero? If lambda is 0, then let me give a name to this equation. Yeah, equation 2. Then equation 2 is A times V is 0 times V. 0 times V is a 0 vector. 0 vector. Now from here, A is invertible. Now multiply A inverse to the equation from the left-hand side. From the left-hand side. Then A inverse A cancel. It is an identity matrix. A matrix times 0 vector is 0 vector. So V is 0. Contradiction to V non-zero. Yeah, V is non-zero. Okay, non-zero. So if lambda is 0, then we will have a contradiction. So therefore, lambda must be non-zero. Okay, now lambda is non-zero. Now I saw that lambda inverse is an eigenvalue of A inverse. How? Okay. All right. Start with equation 2. Yeah, equation 2 is here. Okay. Yeah. A V lambda V. Okay. Okay. Now, let me move A to the right side. Move A to the right side. That means that multiply the equation by A inverse from the left side. Yeah. Okay. Now, lambda is just a number. I can move the number out. Number out. Okay. Lambda, I know it is a non-zero number. Now, move lambda to the left side. Then we get this equation. 1 over lambda times V. But when this equation is true, yeah, when this equation is true, by definition, the scalar is eigenvalue. So this equation implies that 1 over lambda is an eigenvalue of A inverse. So we have proved this statement. Okay, if A is invertible, lambda is an eigenvalue, then lambda inverse is an eigenvalue of A inverse. This is example 1. Now, second example. Second example. Example 2. Example 2. So that if some matrix whose square, what A square is, A square means A times A. If A square is the zero matrix. Zero matrix. All the entries in the matrix are zeros. Zero matrix. This statement says that A squared is a zero matrix. Okay. If A squared is the zero matrix, then all the eigenvalues of matrix A are zeros. The matrix A has no non-zero eigenvalues. Okay. How to prove this statement? Okay, yeah. So, okay, now let me arbitrarily pick an eigenvalue of matrix A. Let lambda be an eigenvalue of matrix A. Now, I will show that lambda must be zero. Okay, because lambda is an eigenvalue of A. By definition, there is some non-zero vector V such that A times V is lambda times V. Okay, this is definition about an eigenvalue. Right. Now I start with this equation. I multiply this equation from the left-hand side, don't from the right-hand side. From the right-hand side, V times A not computable because the size is V times A. V is n by 1. A is n by n, not computable. So multiply A squared from the left side. From the left side. So we get A squared V. Okay, move out lambda. Okay. Okay. The right side, A times V is lambda times V. Lambda times V. Okay. A squared V. The right side, lambda times V. Lambda squared times V. Okay. Now, we are given that A squared is a zero matrix. So zero matrix times vector V is lambda. So we get a zero matrix times a vector is a vector, zero vector. So we get lambda squared is equal to zero vector. And it is important to remember eigenvector non-zero. Non-zero, that means that at least one entry is non-zero. Say 1, 0, 0, 0. Yeah, non-zero. A lambda times a non-zero vector is zero vector. So the number must be zero. So from here, lambda square must be zero. This number must be a zero number. Okay, zero number. Okay, now take square, lambda is zero. Take square root, lambda is zero. So therefore, any eigenvalue of matrix A is zero. Is zero. So I have proved this statement. This is a second topic. Now, third topic. Let me see what is. Some questions are coming. I am so confused. Question. Okay. What question do you have? Substitution from the equation given in definition. What do you mean substitution from the equation given in definition?
So I think they're asking how we went from lambda times AV to lambda squared times V. I was just saying it's from substituting from that first equation that we have.
Oh, yeah. Here, I plug in this equation here to get this. Is this your question? I have this equation. Then I multiply this equation from the left side to get this equation. Because this is a number, I can move this number out. Oh, okay, good. You got the point. Okay, you got the point. Yeah, because this is a scalar, so I can move the scalar out to get this equation. Then again, A times V is lambda times V, so I get this equation. A number times a vector is number squared times a vector. I get this equation. But A squared is given to be a 0, so I get this equation. V non-zero. A number times a non-zero number. A number times a non-zero vector is 0. The number must be 0. I get this equation. So lambda is 0. Because lambda is arbitrary pick. So all eigenvalues of A are zeros. This is a topic 2. Okay, now topic 3. What topic 3 is? Oh, topic 3 is a topic from section 2. In this topic, I want to answer this question: how to find all eigenvalues of a matrix? Okay, now let me answer this question. Okay, topic 3. Topic 3. Given a square matrix, square. Okay, we only consider square. Okay, matrix for eigenvalues and eigenvectors. How to find all eigenvalues? I want to answer this question. The answer is based on the following 2 observations. Okay, observation 1. If a scalar eigenvalue is a scalar, if a scalar, say I call the scalar lambda 0, is an eigenvalue of matrix A, then by definition, A times some non-zero vector is equal to this. Okay, for some non-zero V, non-zero vector V, right? Okay. Okay. Now let me give a name to this equation. Say equation number 3. Okay. Now let me move the right side to the left side. Okay. Then we have this. Okay. Equation 3. Equation 3 implies the following equation. I move the right side to the left side. The right side is a vector. I move the vector on the right to the left. Then the right side is 0 vector. Now let me take out the vector V. Okay. Before I take out the vector V, don't forget, write the second term as lambda times identity matrix times B. Otherwise, A matrix minus lambda 0, a number not computable. Okay. Right. Now let me take out. about this equation, remember this guy non-zero. A matrix times a non-zero matrix, non-zero vector is 0. The matrix cannot be invertible. A submatrix times a non-zero vector. Yeah, this is a non-zero vector is 0. Then M, this matrix is not invertible. Why? If M is invertible, then I can move it to the right side. If M is invertible, okay. How to move M to the right side? Multiply M inverse. Then M inverse times M is I. Matrix M inverse times 0 vector is 0 vector. If a matrix times a non-zero vector is 0, then M is not invertible. Otherwise, we will get a contradiction. We will imply V, the vector, must be 0. A contradiction. Okay. So therefore, we have this equation. Therefore, A minus lambda 0 I is not invertible. A matrix is not invertible. Determinant is 0. Okay, so determinant is 0. Determinant determines whether a matrix is invertible. Okay. So observation 1, to answer this question, 2 observations. Today I only have time to present observation 1. If this number is an eigenvalue of A, then A minus the number times I, this matrix determinant, must be 0. Next Tuesday, I continue with this topic 3.